This lecture is brought to you by CNCB Academy of Science and Technology. Visit us at cncbacademy.com.
We are going to start today's lecture on electromagnetism for Ph.D. entrance exam. This is the second part of the lecture, and I am Devsis Anand from the Department of Physics. Let's get to the first problem. So this is the first problem. A rectangular dielectric slab partly fills two identical rectangular parallel plate capacitors which are maintained at potentials V1 and V2, with V1 greater than V2. The slab can freely move without friction in the space between the capacitor plates, filled with air. Show that the slab will move towards the door of potential. So what's the figure? This is the figure. So this is the dielectric slab, and these are two capacitors. This capacitor is at voltage V1 and this capacitor is at voltage V2, such that V1 is greater than V2. And this capacitor has some capacitance C1 and this capacitor has some capacitance C2. And this slab can freely move in this space. So the question is, if the slab is free to move, then in which direction the slab is going to move? And this is so what is the idea? So idea is we have to find the total energy of the slab. So and then we have to take a derivative. So what do I mean by this? So total energy of the system, total energy of the system is E1 plus E2. So this is my E1 and this is my E2. This is my system 1 and this is my system 2. So let us consider, so what is the energy of system 1? The energy of system 2 I have written first. This energy of system 2 is, so it is half CD square. So let us consider this. So let us consider this distance to be x. Okay, this distance, the slab is inside the second capacitor by a distance x. So this is x. So what is the capacity? And if the breadth of the system is b, it has a breadth is b, then the energy of the system is half CD square. So what is the capacitor? What is the capacitance of this part? So what is the capacitance of this part? This part is epsilon r x b by d. B is the separation, and b is the breadth. X is this distance. Right. So this is half C V2 square. So this is for the this capacitor, and we know that if two capacitors, this and this, are arranged like this, then the equivalent capacitance is this. So it will be this plus this. So what is the capacitance of this? What is the capacitance of this? The capacitance of this will be your epsilon naught L minus x b by d. So L, what is L? This is L. So let us say that this total length is L. Okay, this total length is L. So L minus x is the length of this capacitor and times breadth. So this will be epsilon naught L minus x b by d. This is the capacitance of C2. So V2 square. Similarly, what is the, so this is the E2. So what is the energy of the system 1? System 1. So system 1 is, and okay. So let us consider this. So if this total length is capital L, the length of dielectric slab, and this is x, then this is L minus x, capital L minus x. So what is the capacitance of this? The capacitance of this is epsilon r L minus x into V by D. And what is the capacitance of this? C1, what is C1 here? C1 will be epsilon naught, then L, this is L, okay, from here to till end is L. So L minus x is this length, and times B divided by D. And again the arrangement is such, so if these two capacitors are like this, placed like this, then the equivalent capacitance is this plus this. So that's what this plus this and times V1. So half equivalent capacitance into V1 square. Here half equivalent capacitance into V2 square. So this gives me the energy. So from here I can find the force. Force is minus d dx, and from the, so we have to find the sign of F, if the F is positive or negative. Remember, V1 is greater than V2 and epsilon r is greater than epsilon r. So the sign will tell whether this dielectric will move in this direction or this dielectric slab will move in this direction. So if F is positive, so if F is positive, that means it's going to move in this direction, sorry. And if F is negative, then it is going to move in this direction. That you have to find out. So this is, so dE dx is easy to find out. You have to complete it. So E is A1 plus E2. So complete this and check the answer. So what is the second problem? A flat film has uniform thickness of 510 nanometer. White light, so this is the range of white light, 390 to 700 nanometer is incident normally on the film. If the refractive index of the soap is 1.33, then show that the dominant color of the reflected light is green. So you have a slab, so light will be normally incident and it will get reflected. So it will get reflected from the top surface and the bottom surface. So the total optical path is 2 times NR. NR is this one, refractive index, times D. D is the thickness. Thickness is given, 110 nanometers. And for constructive interference, this is the condition, right? N plus half lambda. So what we have to do, we have to just check. So we have to be in the visible region. So you change n and see for which value of n you get lambda in the visible region. And from there you have to choose the lambda which is in the visible region and what is the corresponding color of that lambda, and it should be green. The reflected light is green. So whatever, so you fix change n and see what's the value of lambda and choose the value of lambda which lies in this region, in this range, and find out the color of that lambda. So next problem is a monochromatic linearly polarized light with electromagnetic field x plus y is incident normally on a birefringent crystal. The wavelength of the light is 500 nanometers and the refractive index of the crystal along the x and y directions are 1.66 and 1.49. if the thickness of the crystal is 4.34 nanometers, show that the emerging light will be electrically polarized. So here, when it falls, so when the light is incident normally on the calcite crystal, so it will be, so we will have two rays. One is extraordinary ray and one will be ordinary ray. Extraordinary ray will be, say, will vibrate to say along. So it will either vibrate, say if extraordinary vibrates along x direction, then the ordinary ray will vibrate along y direction, and the two rays will have different velocities, because the refractive index are different. So once it's incident on the calcite crystal, the ordinary ray will be, say, along, if the ordinary ray is along y direction, the extraordinary ray will be along x direction, and they will travel along the crystal, along the crystal normally, but with different velocity. And so there will be a phase difference between them when they come out. So what is the nature of the emerging light? So we have a linearly polarized light. So linearly polarized light is incident. So part of it will. So when a linear polarized light is incident, so this is the, so one part will be, say, along. So one component will be along x direction inside the calcite direction, and the other component will be along y direction. That's how it will break. So what is the path difference? Path difference is so this is delta. Delta is the thickness of the calcite crystal, and delta n is the difference in the refractive index. So that will give me the path difference, right? Optical path difference. And so lambda is known. So what is lambda by delta L? I find out the fraction. So from here I can find out delta L as a fraction of lambda. And we know that lambda means a phase difference of 2 pi. So delta L corresponds to how much of phase difference? Right? Delta L corresponds to how much of phase difference? That you can directly find from here, and this will give the phase difference between two beams, and that's the state of polarization. So the two beams, the amplitude of the two beams will be the same. The one along x will have the same amplitude, and the one along y will be having the same amplitude. But there will be a phase difference, and so what is this phase difference? And that you have to find out. And once you know the phase difference, you can easily guess what will be the state of polarization. If the phase difference is pi by 2, then you would have said that it is a circularly polarized light. If the phase difference is pi, then you could say that it could be a linearly polarized light. So in this case, what is the phase difference of the emerging light? Next problem. Consider a sphere of radius r containing charge with volume density rho r is equal to 4 pi epsilon naught epsilon divided by r. The charge is 0 outside the sphere. The electromagnetic potential is given by phi and a inside the sphere. We have written in many ways. We know that this is gauge field, phi and a. Show that phi is equal to 0 and a is equal to 2 alpha tr represents the distribution correctly. So what we have to find out is the electric field and magnetic field for this problem. So the electric field can be found out using Gauss's law from here. Right? 4 pi, so you take a surface of say radius r, and then 4 pi r square into E, symmetric, 4 pi r square into E will be the total charge that is enclosed within the sphere. So rho r is given, so you can find the total charge that will be enclosed in this sphere. And from there you can find out the total charge, and hence you can find out the electric field. Electric field will be radially outward, and the magnetic field is 0. So check, and what you have to do? So electric field we know. So electric field is minus grad phi minus del N T, and B is equal to curl of E. Check whether, so you know E now. So check whether this satisfies the value of E, and B is trivially satisfied. So that's what you have to check. So now another problem. An ideal polarizer is placed between two crossed polarizers in a coaxial geometry as shown. The middle polarizer is rotated with an angular frequency omega about the common axis. If the unpolarized light of intensity I0 is incident on the system, show that the emergent intensity of the light is I0 by 16 1 minus cos for omega t. So this is the figure. So suppose light is incident, this is a linear polarizer, then we have another linear polarizer which is rotating, and then we have another linear polarizer. So these are crossed. So this and this direction make an angle of 90 degree, and here the direction of polarization direction is rotating with some frequency omega. So how do we find out? This type of problem we have done before. This is, so once this light, unpolarized light passes through the first polarizer, what is it? What is the intensity? I0 by 2, that we know, that we have already discussed. And then from the second, this one. So this one, if it makes an angle of omega t, right? Say at t is equal to 0, this was aligned like this, the direction. So after time t, it has rotated omega t. So the amplitude or the intensity that comes out of this polarizer is I0 by 2 cos square omega t. And so what is the amplitude that we get from the last polarizer? This one. So if this and this direction make an angle of omega t, then this direction and this direction make an angle of pi by 2 minus omega t. So the amplitude that comes out from the last polarizer will be this times cos square pi by 2 minus omega t, which is this times sin square omega t, and from here you have to go here, and that is for you to complete. Okay, so this problem, consider a spherical shell of radius r having a uniform surface charge density sigma. Suppose we construct a spherical Gaussian surface having the same radius r, but its center is shifted from the charge radius by a distance r. Okay, here also it will be, I think, capital R. This is not small r, this is capital R. So, but its center is shifted from which I show that the electric flux to the Gaussian surface is pi r square sigma by epsilon. So what do you mean by that? So this is my, so this is the charge. So what is it? So this is my spherical shell having a uniform charge density sigma. It has a radius r. And we construct an imaginary surface, a Gaussian surface, such that the center, the distance between the center is also capital R. Now what the problem we have to find out is, so if you want to find out the electric flux through this Gaussian surface, what is its value? So in order to do that, what you have to find out is, this Gaussian surface encloses this charge, the charge that is on this surface, right? So what we have to find out is basically the surface area of the charge. So is the surface area of the sphere that this. So this is a sphere. This is a sphere. So these two spheres are they're crossing each other. Okay, they're intersecting each other. So we have to find out the surface area of this. The surface area of this sphere. Once you find the surface area, we can find out the charge that is enclosed, and then after that it's trivial. You can easily find out the flux, electric flux across this Gaussian surface. So this is a two-dimensional figure. So the three-dimensional figure, actually the surface will look somewhat like this. Is it not? The surface will look somewhat like this. So how the surface look like? This is a sphere. So on the sphere you draw a circle. So the right hand of the circle will be the surface of interest. So now you have to find out the surface area of that surface. So how do I find out? So consider two strips separated by d theta. This is my theta. So what is the area of this circular strip? It will be 2 pi r sin theta r d theta, right? So if this is r, right? If this is r, then this is r sin theta. So the radius of the circle is r sin theta. So the circumference is 2 pi r sin theta. 2 pi r sin theta into, then what is the width of the circle? It is r d theta. So the total area of this infinitesimally small strip of the circle is 2 pi r sin theta r d theta, and then we have to integrate over theta. So theta will vary from theta is equal to 0. So theta is equal to 0. That's fine, to some theta, from theta max. And what is the theta max? Convince yourself that the theta max is 60 degrees. That you can find from here. Theta max, so this is my line joining the two centers, and if I draw a line from this point to this point, this angle will give me theta max. Convince yourself that this angle is 60 degrees. That's it. And you will get the total surface area, and from there you will get the surface charge, and from there you will get the total flux across this field. This is another problem. A circular ring of radius r with total charge q ring. So it's a ring has a uniform linear charge density. It rotates about an axis passing through its center and perpendicular to its plane with constant angular speed omega. The magnetic field at the center is found to be B0. Another thin circular disk of same radius r has a constant surface charge density with total charge q disk. So this disk too rotates about the same axis as the ring with the same constant angular speed omega. The magnetic field in the center in this case is 10 to the power minus 3 times B0. Show that Q ring by Q disk is 2 into thing. That is the ratio of the charges. So this is not difficult. Only this thing. So if you take a ring and if the total charge on the ring, so ring is uniform, is Q ring, then you have to get the current. Current is total charge into frequency. Frequency is the number of revolutions per second of the ring. That means this amount of charge flows across a particular point per second, and that is the current. And F is related to this. F is the omega by 2 pi. This we all know. So what is the magnetic field at the center? So magnetic field at the center will be due to this ring is mu 0 I ring divided by 2 r. In this case, if you consider the first case, B ring is B naught. B ring is equal to B naught. And in the second case, you have to find the B at the center. So basically you have to integrate over. So you have to integrate over this thing. B ring, for if you just consider an infinitesimally small ring, circular ring. Okay. So for that there will be a magnetic field. In that case, I ring will be is equal to 2 pi r into dr into sigma, and then you have to integrate over r from 0 to capital R. This is straightforward, and then you will get the V due to the disk, and then you compare B disk and B ring. So this is another problem. Consider an isolated magnetized sphere of radius r with uniform magnetism m along the positive direction, with north and south poles of the sphere lying on the z-axis. So it is given that the magnetic field inside the sphere is B is equal to 2 mu naught by 3 m vector. Okay, m is the direction of magnetization inside the sphere, and it is a constant vector. Show that the bound volume current density is 0. Show that the surface charge density has maximum magnitude at the equator. And far from the sphere, the magnetic field is due to the dipole moment, where m by 4 pi r cube is equal to b by 2 mu 0 z cap. So what is the surface current? Surface current is given by curl of m. Here m is uniform and in a particular direction. So curl of m will always be 0. And what is the surface current relation? Surface current relation is n cap cross n. So on the surface, n is the unit normal vector on the surface. So on the equator, this unit normal vector is in the equatorial plane and projecting outward, right? And m, so m is along z direction, so n and m are perpendicular. But this happens only at the equator. N is the unit normal to the surface, so unit normal to the surface and m are perpendicular. And that's it. That's why the surface current will be maximum at the equator. So, and the third question is, very far away from the sphere, actually you don't see the sphere, dimensions of the sphere. What you see is just the total magnetic moment of the sphere. Right? So total magnetic moment of the sphere is 4 pi r cubed by 3 is the volume of the sphere times magnetization. Magnetization is magnetic moment per unit volume. So this is the total magnetization of the sphere. That is what at a very far distance you will see. You will not see the radius r. You will just see a magnetic dipole of having magnetic moment this. Okay, this is M is magnetic moment per unit volume. So this is the total magnetic moment. That's it. You can find out. So just you have to substitute the value of M from here, and you should get this answer. So we will go to the next question. An electric field as a function of radial coordinate r has the form E is equal to alpha e to the power minus r square by r cap, where alpha being a constant. The electric flux through a sphere of radius √2 centered at the origin is phi. Show that phi by 2 pi alpha is equal to 0.3. So you consider a sphere. So the electric flux across the sphere will be, so r square sin theta d theta d phi is a surface area on the sphere of radius r. So E into this infinitesimal surface area, and then you integrate over all theta and phi. Remember, r is constant here and the value of r is given here. This is √2. So you find out phi and you check whether this is correct or not. Okay. R is constant here because we are finding the flux across the surface of the sphere, and this is actually the infinitesimal surface area of the sphere with radius r. We go to the next problem. Young's double slit experiment is performed using a beam of 660, which is called fullerene molecules. Each molecule will be made up of 60 carbon atoms. When the slit separation is 50 nanometers, fringes are formed on a screen kept at a distance of 1 meter from the slit. Now the experiment is repeated with C70 molecules instead of C60, C70. So there are 60 molecules of carbon. Here there are 70 molecules of carbon with slit separation of 92.5 nanometer. The binding energy of both the beams are the same. This is a given problem. The position of the fourth bright fringe for C60 will coincide with the nth bright fringe for C70. Show that n is equal to 8. So here we need two things. This is given. Kinetic energy is the same. So this is for fullerene. So P1 squared by 2y1 is the kinetic energy of fullerene molecule, and that should be equal to the kinetic energy of C70 molecule, P2 squared by 2y70. And the Brock development is lambda 1 is equal to h by P1 and lambda 2 is equal to h by P2. P1 is the momentum of fullerene and P2 is the momentum of C70. That's it. And these relations are from Young double slit. So D1 is the distance between the slits. X is the distance of the screen, and capital D is the distance between the slits and the screen. So here it is given for fullerene, for the fourth maximum, this is the condition. So if I go to C70, we want them to get, we want the two fringes to coincide. That is, so d2x will be the same here. d2 is the difference between the slits for C70 is the same d. That should be equal to n lambda 2. And from here you can just use this relation and you can find out what is n. So that will be, so you will get things in terms of m1 and m2. So m1 is the mass of one molecule of C60 and m2 is the mass of one molecule of C70. And you know the ratio. From here it's obvious what is the ratio. Here you have 60, one molecule has 60 carbon atoms, here one molecule has 70 carbon atoms. So it's not difficult. To the next problem. Two independent electrostatic configurations are shown here. The two configuration 1 consists of an isolated charge Q is equal to 1 coulomb, and configuration 2 consists of another point charge surrounded by a thick conducting shell of inner radius R1 is equal to 1 meter and outer radius R2 is equal to 2 meter, with the charge being at the center of the shell. So given W1 is equal to epsilon naught by 2 E1 squared by dV, and W2 is equal to epsilon naught by 2 E2 square by dV, where E1 and E2 are the field corresponding to the two configurations. The volume integration is carried out over the whole space. We'll show that 8 pi epsilon naught W1 minus W2 is equal to half. So you have to do the first integral for this configuration, and the second configuration is charge. Then we have a conducting, so this part is conducting, and then after that again, so this is a tube of conduct. It's a tube, no? This is a solid conductor. So E is electric field is 0 here, right? So what you have to find out is this. So of course in the first case, we know E is equal to 1 by 4 pi epsilon naught R square. So in the first case, if you do this integral, you will end up with this. Limit r tending to 0, 1 by 4 pi epsilon naught, 4 pi by r, where r is tending to 0, because at the limit r tending to 0, the integral will look like this. That is 0. And from r infinity, it will be 0. So this is, so Wi is equal to this. Similarly for this one also, we know what is the electric field, the same electric field. So first you have to integrate from this to this, and then you have to integrate from this to infinity. So when you are just integrating from this to this, you will again get this kind of expression in W2. Okay, you will get in W2, you will get this kind of expression. So this thing blows up, but when you do W2 minus W1, this from W1 and this from W2 cancel out. You can check yourself. It's not difficult. So do this integral, and so this integral, do this integral. So from 0 to this. So R1 is equal to 1, again from R2 is equal to 2 to infinity. We have to do this integral. Remember, you have to square it and then integrate. And check what you get. We expected to get this half. This is the last problem of today. So consider an electromagnetic wave propagating in the z direction in vacuum with magnetic field given by B is equal to B naught equal to I kz minus omega t. So you have to take the real part. B naught is given t to the minus 8 Tesla, 10 to the minus 8 Tesla. The average power passing through a circle of radius 1 meter placed in the xy plane is T in watts. If epsilon naught is 10 to the minus 11 in SI units, show that the value of 10 to the power 3 P by pi is half. So first we have to find out the average, average pointing vector, time average. So pointing vector is 1 by mu naught E naught cross B. We know the relation between E naught and B naught. E naught is equal to C B naught. Okay, so if B naught is given, so we say B is equal to B naught cos kz minus omega t, then E is equal to E naught sin kz minus omega t, cos kz minus omega t, and E and B are mutually perpendicular, you know that. So from there, you can find out the pointing vector average, and remember we have to do a time average over one period. If you find out this expression, we will get half. Check. So you will get S average. And once you get S average, you multiply it by pi r square, the area of the circular radius, the area of this circular area, and that will give me the power that is crossing that area, or the energy that is crossing the area per unit time. So that is P, and this is check 10 to the power 3 P by pi. What is the value? Remember, epsilon naught is given, so you can actually multiply this thing. You can multiply by epsilon naught and divide by epsilon naught and multiply by epsilon naught, and again 1 by mu naught epsilon naught is c square. So we can use these relations and find out what is this expression. And okay, we will not do this problem. We will do this problem later. We'll stop after doing this problem. So consider a solenoid of length L and radius R, where R is much less than L. A steady current flows through the solenoid. It is known as the magnetic field inside solenoid is uniform and zero outside. Justify the graph given below, which shows the variation in the magnitude of the vector potential. Okay, so this is the vector potential is given. This is in cylindrical coordinates. So it has only 5 components. No R component, no Z component. Z is equal to L by 2. So what you have to find out? That you soon see a graph, and you have to justify that graph, which shows the variation of the magnitude of the vector potential as a function of the radial distance r in cylindrical coordinates. Okay. So we have to find out how a phi. So this is the solenoid. This is a long solenoid. L is much greater than. So L is much greater than R. And L by 2 is not important here. L by 2 means you are well within the solenoid, and this end effects are negligible. So basically field is uniform here, and this is A phi and this is R. So you have to justify that this is correct. this kind of, with the, this graph is correct. So how do I justify it? It's simple. So curl of A is already given. So this is given. So curl of A is B, and we know that B will be only in the Z direction. Right? So this will be 0, this will be 0. So we have to be interested in only this direction. AR is 0, right? AR is 0. So only term that is of importance is this one. So we want B to be uniform inside. That means uniform inside means this term will be independent of R. How can it be independent of R? It can be independent of R when A5 goes as R. When A5 goes as R, then it becomes del R of R square. So we will get R, and that R and this R will cancel, and what we will get is a uniform, a constant magnetic field in the Z direction. And so this is inside. See, this is inside the solenoid. Outside the solenoid, I want B to be 0. So that means this del, so this has to be some constant, and the derivative of the constant will be 0. So how can it be constant? If A5 goes as 1 by R, then R cancels, there is no R dependence, then del R will be 0, and hence we will get 0. So, so here inside the solenoid, A5 goes as R, so linearly increasing, and then outside the solenoid, A5 goes as 1 by R. So it is like this. So that is how we justify. And we will end today here, and we will soon meet again for the third part of this problem on this electromagnetism for Ph.D. and subjects. So thank you.